and we're now recording. All right, so it's my pleasure to introduce Nadya Mason. She comes to us from the University of Illinois at Urbana-Champaign, where she's a professor of physics. Nadya is a leader in the field of condensed matter, experimental condensed matter physics. She did her doctoral work at Stanford, and she was a postdoctoral fellow at the Harvard Society of Fellows. She's made important contributions to the study of low-dimensional materials like nanotubes, graphene, topological insulators, and nanostructured superconductors. She's a recipient of the Maria Goeppert-Mayer Prize of the American Physical Society for her contributions. And I guess one more thing you should know about Nadya is that she excels at everything she does. Before she took to physics, she was a world-class gymnast and on the US national team. So
years ago, many years ago.
Right, it's still very impressive. It doesn't become less impressive. So welcome, Nadya. We're very happy to have you here today to tell us about strained graphene. And
thank you. It's a huge pleasure to be here. And let me share my screen. Oh, you need to enable screen share. Otherwise, it's going to be a very boring talk. I guess I could give a Blackboard talk, but pictures are better. Here we go. Okay, let me put this in. Okay, you guys seeing my actual screen?
Yes.
Excellent. Okay, great. Good. So it's a pleasure to be here. I'm sorry I can't be there in person. I guess everyone understands why at this point, but hopefully we'll get a chance to all see each other in person again some point in the near future. In the meantime, I'm happy to talk about electron transport in strain-engineered graphene. And these are just some of the papers that I'll be talking about today. You can see it's a topic we've been working on for some number of years now, just kind of building up little by little. And because I know that it's hard to pay attention to all of a Zoom talk, I'll start by summarizing the entire talk. So the basic idea here is that strain modifies graphene's electronic properties. So then our goal is to create global strain to modify transport, which means we have to, we don't want to modify just the local properties. We want to see these modifications when we put a current across the entire device. So what I'll talk about are some techniques we've developed to nano-engineer substrates to impart strain to graphene on a global scale. This allows us to make controllable global strain. We see effects of strain like superlattice behavior in this strained graphene, a strained superlattice, and we see pseudo-magnetic field effects. And I'll talk about all of this. Okay, so why do we play with strain? Well, one goal is to make new electronics, not just by making elements smaller, but by making them flexible, right? So the electronic devices that we all know and love, like the computers and the phones, these are of course based on silicon. Silicon is rigid, it's brittle. So all the devices made from silicon, or most of them, are also brittle. I don't know why this is I hope this isn't some weird. Okay, we'll just leave it like this. Okay. So silicon is brittle and the devices based on it are brittle. But in recent years, there's been increasing excitement about making flexible, deformable electronic devices where the deformability not just makes it convenient, but also increases functionality. Right. So here, I mean, not just the flexible phone. I don't know if you guys remember, maybe earlier this year, this company came out with a flexible phone that just when the early critics tried to bend it, it broke. I think they had some screen on it that they were supposed to leave on and they didn't. But okay, so we'll get to the flexible phone at some point. But I think there's also other things that we can create. Like as you see here, we can have wearable electronic tattoos that conform to our skin that help us better sense for medical devices. For people like me, glasses that don't fall off every time you try to use them at night that actually conform to your eyes. I'm actually going to fix this. I feel like this is in some sort of weird slideshow mode that I do not like. So, nope. Okay, I'm just going to try it again. Hope that it works this time. Okay, try this again. Okay. So the goal here is to make deformable, flexible electronics that increase functionality and actually make our lives better, have things that are more useful and improve many aspects of our lives. Okay, so to create these flexible devices means uniting nanomechanics with nanoelectronics. Okay, so there's a grand challenge here of combining the electronic design capability of hard materials with the adaptive nature of biology. Okay, and then the physics goal is to understand how the functional properties of nanomaterials and interfaces are tuned by these large multi-scale deformations. So you can ask, well, what materials can we use? Well, you can start by looking at our inspiration, which is the biological materials. And here you see a lipid bilayer, and it has a bending scale proteins inside a lipid that are moving around. And then you can see underneath a 2D material, which has a bending energy on a similar scale. Okay, so now you can see how 2D materials can be really unique. They're actually comparable to the bending of biological molecules. And usually there's a trade-off between flexibility and mobility, right? Biological molecules are not very conductive, so they're not great for electronics, whereas silicon materials are very conductive, or semiconductors, but are not flexible. And you can see in this graph here that if you have something like the typical silicon, gallium arsenide, hard semiconducting materials, they have a very high bending stiffness, but their mobility is very high. But now you can see there's a sweet spot with these 2D materials like graphene and molybdisulfide that have a very low bending stiffness, but also a very high mobility. So these are really an outstanding choice for a new generation of flexible nanoelectronics. And please feel free to interrupt me if you have questions. I will try to be able to, I don't know if I can see the chat actually. Here it is. I will keep the chat open so I can see any questions that you guys have along the way, but please feel free to ask things. Okay, and I am going to try to change to a laser pointer also that you can see. Can you see my laser pointer also? Yes, okay, excellent. Okay, so among the 2D materials, I think that graphene still stands out. Graphene is maybe the original single atomic layer material that generated a Nobel Prize a number of years ago, but it still stands out because of its really amazing properties. So graphene, to remind you, is a sheet of carbon, which is just one atom thick. It's the ultimate limit of a 2D electronic material, and also it's a single atomic membrane. So as I mentioned, graphene is probably, I think, it's easy to produce. That's another great thing about it, especially for experimentalists like me. If you have something that's easy to produce, you can make it cheaply, you can make it easily, you can make lots of devices. That's a huge benefit. So graphene is a single layer of carbon. It's basically pencil graphite you can just take Scotch tape and peel off layers till you end up with a single layer, and that's your single atomic layer of graphene. This is probably the cheapest Nobel Prize that was ever produced. You just need Scotch tape and a pencil in theory, and that generated a Nobel Prize. Okay, they did much more than that, but in theory, it's still the cheapest one you could do. And these days, it's also made using chemical vapor deposition, which is a relatively simple deposition system that combines high temperatures, a carbon source, and a catalytic substrate, typically copper. And that allows you to grow graphene on pretty large areas. And this is what we generally use because then we can transfer it onto different types of substrates. Now, graphene, as I mentioned, has really outstanding properties and applications. Here I just mentioned some of them. It's ultra thin, it's impermeable, has high thermal conductivity, high stiffness, flexible, high current density, high charge mobility, low carrier density, has interesting physics effects like chirality or pseudospin. And the applications are large: transparent electrodes, solar cells, sensors, biodevices, and mechanical devices. So graphene still has a lot of potential uses, I think. Now, we care about the electronic properties of graphene, so I'll say a little bit more about that. So this is the famous band structure calculation on the left here by Wallace that was done in the 40s, I believed, and 1947, and then was basically kind of ignored for 60, 70 years until now. It's one of the best cited papers ever after graphene was experimentally discovered in isolated form. But he showed that the energy of graphene is given by two carriers. The energy of the carriers in graphene is given by two surfaces above each other, as you can see here. And then these surfaces touch at single points. This is the Dirac point of graphene. So what does this mean in terms of measuring conductance? It means that if you measure conductivity versus gate voltage, you get this linear energy versus momentum around these Dirac points. So graphene is a semi-metal. Its conductance doesn't go to zero when you apply a gate voltage, but it does go to a minimum of zero. Okay. what did I say? The conductance isn't pinched off entirely, right? Like a semiconductor. It's not flat, but it goes to a minimum and then rises on either side. So you get a minimum conductivity with a linear conductivity around it. So it's a semi-metal with a gate tunable conductance. Now, why is this important? This is important because graphene is unique in having high mobility, low density, and gate tunability. And you can think of this in terms of standard metals like, say, copper or something, right? Copper conducts really, really well. It has a high carrier density. But because it has so many carriers, you can't deplete its carriers with an electrostatic gate. So you never see copper as a device that you can turn on and off because it has too many carriers to turn off. On the other hand, you have something like a semiconductor, and this is gate tunable, but the mobility isn't very high. It's not ballistic. You get a lot of scattering in these materials. And so graphene kind of bridges this gap by being both gate tunable and high mobility. Okay? You also have these Dirac points, which can shift depending on what you do to them. So if you dope graphene or strain it, then by doping, I mean you apply either electrostatic doping, or generally if you say put a chemical on it that adds carriers to the graphene, the Dirac point will shift. Okay, so then automatically graphene becomes a really interesting electromechanical and chemical sensor just by moving that Dirac point around. And that's the basis of a lot of graphene sensing devices. Okay, but we care about strained graphene. So the question now is, how do the electronic properties of graphene change when it's strained? Okay, so the answer is they change a lot, right? So straining graphene strongly modifies its electronic behavior. And this is an old paper by Castroneto et al., but it predicts a lot of really interesting and useful electronic behavior, such as energy gaps, quasi-magnetic fields, new types of transistor type behavior just from straining the graphene. And here I'm going to give an example, which I think is one of the best examples of how to modify materials properties with strain. This was an example where it's a scanning tunneling microscopy experiment where graphene was just put on a surface and they happened to find little nano bubbles on the surface, bubbles that were of the order of a couple nanometers in height. And then they did scanning tunneling spectroscopy on top of these bubbles. And when they did that, they found the electrons were circulating around these bubbles in the same way that they'd circulate in an ultra high magnetic field. So around this very strange graphene, the electrons were moving as if they were in a 300 Tesla magnetic field, right? That's a huge magnetic field, right? Somehow, even without applying an external field, you're getting the electrons and the electronics behave as if they're in a 300 Tesla field. And 300 Tesla is really large. Okay, so just to give a sense of scale, in the lab, you might get a field of 20 Tesla if you're willing to pay $300,000 for a magnet. An MRI magnet might be 16 Tesla. And I think the largest field that's been shown on Earth, such that you put a huge current in it and then the magnet blows up, is something like 120 Tesla or something like that. Okay, and that's high enough to make a magnet blow up. So 300 Tesla, to see electronics at that scale is a really, really impressive and interesting thing to do. So, but this was done with scanning tunneling microscopy, not across the device. Now, just want to note that we've been very interested, and a lot of people are interested in seeing these pseudo-magnetic fields, but they do require a non-uniform strain to achieve them. So if you look at the strain field, right here, I have a strain field that has an X and a Y component. The strain field enters into the Hamiltonian of the graphene as a vector potential, basically, right? And because it's a vector potential, you basically take the derivative of it to get the effective field. And so you need something that has X and Y components to it. So only a non-uniform strain will generate these pseudo-magnetic fields. And this also gives you a sense of why the electrons feel like they're in a strong magnetic field. Because what happens is that when you strain the graphene, the electrons basically see different phases going in one direction versus the other direction. And because the vector potential enters as a phase in the Hamiltonian for electrons, basically it enters in the same way that a magnetic field does. Okay, so if you have this non-uniform strain, then you can generate a pseudomagnetic field in graphene where the electrons will act like they're in this high field. Okay, so we've been interested in creating generating this global pseudo-magnetic field because we want to affect transport, right? So to affect transport across a device, not just in one little spot, we want to have a global effect of strain. And we need to fine tune the strain and the shape to get this non-uniformity. And there've been a lot of predictions about how to do this. First, just stretching graphene, right? Or stretching it in 3 directions. You know, graphene's really small. If we had tiny little hands, we could do that, but we can't. Right? So in order to get this non-uniform strain, we want a different method. And it turns out that creating some sort of periodic potential that pins and strains the graphene periodically might be the easiest way to realize this sort of global strain field. Okay. I also want to note that, you know, I'll be talking about mostly creating these sort of nano-patterned substrates to create these periodic strain structures, but there are limitations that we want on the periodicity if we want to see pseudomagnetic field effects. Now, the goal in creating a pseudomagnetic, in seeing and actually observing in transport the effects of a pseudomagnetic field is seeing a shift in this Dirac point, or basically seeing an additional little dip, kind of like the Dirac point. And I'll say more about this later. But in order to see that at an accessible energy scale, you know, something less than applying 100 volts to the sample, you have to have a periodicity of the scale of 10 to 100 nanometers, right? And that means that if the periodicity is too small, then these extra dips and extra features you see are too close to the Dirac point and can't be distinguishable. And if the features are too big, then the additional dips come at too high an energy scale. So in order to see the features in transport due to pseudomagnetic fields, we want to have periodicities on the scale of 10 to 100 nanometers. Okay, and you'll see us focus on this pretty soon. Okay, so now I'm going to take a step back and tell you, like I said, we've been actually working on this for a long time and thinking about ways of globally controlling strain in graphene. And it turns out that global strain is not that easy. So when we first started working on this, I just gave it to an undergraduate, which is the people you give all the really hard projects to. And I said, okay, just take some graphene and stretch it and see what happens. And so he made this really nice, I love this project because it's so visual. He put a piece of rubber, a polymer, inside a stretching apparatus. And here you can just see 2 clamps and a micrometer, right? And made a grid on it and then transferred graphene onto the grid and then watched under a microscope as he turned the micrometer and the graphene was just pulled. Okay, so that's kind of global strain just by stretching the graphene. And okay, so what did we see? What we saw is kind of what you might expect, which is that the graphene actually just ripped. Okay, because we were just applying this global strain thing. So we saw that you know, first that the graphene was unripped, and then as we applied strain, we got a crack that was a little bit bigger. And if you apply more strain, the crack gets bigger. But the interesting thing we found is that when we decreased the strain again, the crack completely disappeared, or almost completely disappeared. So this was something that we found unusual, because usually if you take like a pencil and you break it in half, right, and then you try to put it together again, the crack is still there. But in graphene, it almost disappears. And we measured resistance in this case. You can see that the resistance was reversible. It went up when it was cracked, and then it went back down again when you released the strain. So it's almost like the strains would close up again in graphene, which is something really useful if you're trying to make flexible graphene devices and you worry about it cracking. You know that when you release the strain, it basically goes back to the way it was. So this was something interesting, but it was really making lemonade out of lemons, because we didn't really want cracks. We really wanted global strain and transport effects. So it was something interesting, but it turns out that just stretching the graphene doesn't work well for transport purposes. Okay, so after trying this, we decided, okay, we really want to work with these micro-patterned substrates, like I mentioned. So I had another undergraduate make a project where he made these micro-patterned substrates. So again, sometimes just trying the quickest and fastest thing is really interesting. So what this student did is he went and took just a piece of plastic and made nano indentations in it. There's a little machine called, well, a box-like machine that's a nano indenter, and you kind of press it down. As you can imagine, it makes pock marks where you want across the sample. And so he made these are kind of a couple micron in size indentations, and then he poured PDMS, a rubbery material, and molded it into these indentations and peeled it off. So then what we had were these indentations on the surface of the mold. And then we could evaporate metal or an oxide to make it more rigid, so it wouldn't just bend. And so what we ended up are these beautiful pyramidal type features that are, spaced by a couple microns in height, and we could control the configuration of these and see how the configuration of features affected the adhesion and the strain in graphene. Okay, so we transferred graphene onto this arrangement of these mesoscale features and found that the graphene indeed pinned and strained at the top of the features. Well, how do we know that? One thing we did was atomic force microscopy. And so here you see 3 atomic force microscopy images, where the left one is for the far spaced pyramids and the right is for the more closely spaced ones. And you can see on the left, there's almost no features actually. What this is telling you is that for the widely spaced pyramids, the graphene basically conforms to the pyramids, okay? Because it's not very strained, so it just kind of lies over it like a very soft blanket, okay? However, as you start making the spacing smaller, you start seeing these bright lines in between. See those wiggles there? Those are wrinkles that are formed, and it tells you that the graphene is starting to be strained on the pyramids, and it's releasing the strain by forming wrinkles in between. And then as you make these pyramids as close together as we could, which is a couple microns, suddenly you see these large regions of bright spots, which tells you the graphene de-adheres from the surface. So we've reached a point where the adhesion energy is smaller than the strain, and rather than stay strained, the graphene just pops up. And so what this tells us is that we can control the strain in graphene just by controlling this configuration of features that it sticks to, okay? So this is nice because it tells us that indeed, if we do create this sort of nano-patterned substrate, we can achieve strain over a large area of graphene, which is what we are aiming for. Now, that's good, but it turns out that for one, the nano indentation technique is very time consuming. It's not that versatile. And the PDMS wasn't compatible with electronic devices that we want to make. You can't really make, it's hard to measure transport on a piece of rubber. And we also wanted even smaller features. Like I said, we're aiming for things that are of the scale of 20 to 100 nanometers. Okay, so after showing that we could indeed induce strain, we tried to move to something that was more device compatible and smaller. Okay, so that means that we ended up doing something lithographically. And so this one I started with a graduate student. So after a couple of years of working on it, the project finally graduated to a graduate student working with an undergraduate and making lithographically defined features. So here we want to make something for transport. So we ended up making something on silicon oxide substrates, which is the standard device material. And what we did is we started with a silicon oxide substrate. So imagine this blue part here is just silicon oxide with doped silicon underneath. And we put on copper caps that were of the scale of 100 nanometers, about 100 or 200 nanometers. And then we used those caps as a mask to etch the silicon oxide. Okay, we ended up with these pillars of silicon oxide. And you can see that here in A. This is an array of pillars of silicon oxide. The scale bar is 2 microns. Okay, and then we did a BOE etch. And what the BOE etch is, it sharpens up the silicon. So you can see here that we go from these square pillars to these very sharp pillars when we do an etch. We then put on contacts and the graphene, and suddenly we have a device where the graphene is suspended on these very sharp pillars, and it's patterned for transport. Okay, and here we actually put a hole in here because we try to find regions that aren't ripped. Here I show a ripped region so you can see the contrast between this light gray, which is a suspended graphene, and the dark gray, which is the substrate. Right? And you can see very clearly that the graphene is mostly suspended on top of these pillars, okay, and then patterned here for measurements. Okay, and this was really nice for us because you can see that the scale of each of these pyramids, right? This scale bar is 100 nanometers, and so the tip size here is less than 20 nanometers. So we have very sharp tips and nanoscale pyramids on silicon oxide substrates, sharp features, and for transport measurements. Okay, so you can actually see here the pillars. The dark gray is the graphene, and then these things coming in are our contacts where we make electrical contact to it. Okay, so how do we know? I just said that we put the graphene on it. We knew that when the graphene was on PDMS that it was strained because we could see it adhering and de-adhering from the substrate. But what we really want is not to have adhesion or de-adhesion of graphene. We want the graphene just staying on the top and staying strained. So how do we know that the graphene is strained even when it's just pinned on top of these pyramids? Well, to do that, we use Raman spectroscopy. Okay, so So Raman spectroscopy uses light scattering to measure the energy between different vibrational modes. And in graphene, you have a lattice, you have vibrational modes that go like this. That's the G mode. Is that the D mode? I don't remember. That's the D mode. Oop, that's the D mode, okay, going out. And then there's a G mode where they move in and out. So it's basically just vibrational phonon modes. And you scatter light at the same energy, and you can see how that vibrational modes change. And so then you can understand, okay, so these vibrational modes should change based on the strain in the graphene and the doping. And actually, there's this really nice paper that came out some number of years ago showing that indeed these G lines and these 2D lines shifted when the graphene was strained. However, they also shift if you change the electrostatic environment of the graphene. Okay, so what we want to do is distinguish between changes due to charges and changes due to strain. And what this paper did is it showed that you can differentiate these two by looking at the ratio of how much the G line and the 2D line shift. Okay, so if the ratio of the shift of the 2D to the G is 2, right, then that means that you're straining the graphene. If the ratio of the shift of 2D to G is 3/4, then it means you're doping the graphene. So now we have a way of optically determining how much, whether the graphene is strained or doped, and by how much, just looking spectroscopically. And so this is what we did on our devices. Okay, we can see that we looked at the ratio of the 2D to the G frequency. Okay, pen here. So when you look at the ratio of the 2D to the G, you can see that this line here is the factor of 2 line that shows how things should move if they're strained. And this line here is the 3/4 line that shows what the ratio should be like for doping. Okay, and then we took flat graphene right here. We started here. And then we patterned the graphene, we moved here, and you can see that we moved along a line. Okay, it's red. We moved along a line in that direction, which, as you may note, is parallel to the strain line. Okay, now there's a little bit of doping out here. That's because we got some charge effects from our fabrication, but the bulk of the material really moved along the strain line. And so this tells us that we are indeed straining the graphene that's on top of these nano patterns. It's moving mostly along the strain line. The strain is different from on flat. By flat graphene, I mean that we always have control samples that are not on pillars. Okay, so the control samples that are not on pillars are less strained than the samples that are on pillars. And we can also calculate that we get sort of an average strain of 0.1%, but this is averaged over the whole thing, which means at the apex, we could have a much, much larger strain. Okay, so now we know it's strained, but one of our goals is also to look at transport, right? So we want to see how does the transport differ on flat versus this strained patterned graphene. And so these are conductance measurements. This is a 2D plot where the red lines show you the highest resistance and the blue is the lowest resistance as a function of field and gate. And the thing to point out here is first that this is on the left is for graphene that's on the pillars, and the right is for flat graphene for around the same range. And you can clearly see a difference. In fact, for the flat graphene, we're looking in high magnetic fields, we get beginning of Landau levels, which is field-dependent cyclotron motion. Whereas for the graphene, and otherwise there's no features. This whole region in here, there's almost no features, okay? But here you can see, I don't know if you can still see my, oops, okay, there we go. Okay, sorry, it tried to kill Zoom just because it didn't like my pointer. So here you can see that on the pillars, in fact, we have, instead of just no features at all, we have these high resistance regions of confinement. And we believe that these high resistance regions are due to the strain and the pinning of the graphene on the pillars. Okay. And in fact, we can show that just the pinning alone can lead to some sort of charge variation. So you get a tenting of graphene and this potential difference across the device. And we can show that we expect sort of decreased forward scattering for small regions of confinement along the apex in cases where the path is smaller than the cyclotron radius in the field. And in contrast, a higher field will focus carriers and enhance conductivity. And so we actually see that we have confinement. When we compare the length scales of dots plus our confinement regions, we can see that we have confinement on a scale of about 40 nanometers electronically, which is consistent with the approximate size of the dots that we see in these devices. Okay. So this behavior, this kind of confinement behavior that we see, is consistent with confinement due to pinning regions of the graphene. Okay, so that's one thing. It's a pinning region, but we also see that we have possible effects of a pseudo-magnetic field, which was one of our original goals. Okay, so how do we know we have a pseudo-magnetic field? Well, we worked with our theory collaborators to look at simulations in this case, and you can see that when they simulated the strain at the top of the pyramids, they get a very high and localized areal strain at the top of these nano pillars, and they can also calculate a very high pseudo-magnetic field at the top of these nano pillars. And so that also will confine our carriers. And so we expect to see from these sort of 10 to 50 nanometer dots around the apex, a very high intensity pseudo-magnetic field. And in fact, this had been previously observed, but locally with STM probes in graphene that was on drumhead. So in this case, it was strained by being pinned around a hole. Okay, but when they pinned the graphene around a hole, again, they saw these very high pseudo-magnetic fields. So we would expect something similar in our devices. And we believe that that's leading to some of the confinement. Okay, so this was really useful and interesting, but it wasn't quite as clear as we had hoped. And one of the reasons for this is that the patterns were relatively far apart. If you looked at these patterns of these nanopillars, they're spaced by, I don't know, 300 nanometers or something. That's just because of the way we did lithography. It was really hard to get closer features at first. Okay, so it's promising, but we wanted patterns that were closer together so that the strain dominated, and maybe even have a more scalable technique than having to individually pattern every pillar. And so after working on these pillars, we thought about other things to do and decided that we could use, instead of fabricating things using lithography, which is useful, but sort of tedious, expensive, and time consuming, we could use a molecular self-organization technique to make similar substrate nano features, but much more cheaply and smaller and more effectively. Okay. So here we decided to move on to graphene on closely packed silicon oxide nanosphere arrays. And this is the last technique I'll talk about. And then from here on, I'll talk about the results we have with this, because this has proven to be really a very fertile technique to get a lot of effects out of it. So here we've made graphene that's sitting on top of this assembly of nanospheres, where the spheres are spun onto a substrate from a solution, and they're commercially purchased, and they have diameters down to 10 nanometers and that are variable. So you could just buy solutions of these that are really uniform and have diameters all from 10 nanometers, 20 nanometers, up to hundreds of nanometers. Okay. And you can, this is a molecular dynamics simulation that our collaborators did of this, but they show that the graphene will stick to the top of the pyramids and be strained at the top of the, stick to the top of the nanospheres and be strained there in the same way that they were with the pyramids. Okay. And this is an optical image of what happens when we spin these nanospheres onto our substrates. So when we spin them on, we get these puddles of nanospheres that are several microns wide. And then to do lithography, we align the graphene on top. And so we transfer a sheet of graphene, and then we figure out where it's on top of the nanospheres and then etch away everything but the graphene on top of the nanospheres plus some control samples. Okay. And then here's a measurement that a collaborator, Pinsheng Huang at Illinois, did for us, where she did a cross section. She cut across one of our graphene nanosphere devices and was able to show an image of the nanospheres here, right, with the graphene lying on top of the nanospheres. And so I love this image because it's real. it's rare to see things at the one, you can see this huge scale bar here is 10 nanometers. So TEM is an amazing thing. But you can see very clearly that the graphene is pinned to the top of the nanospheres and then relaxed in between, and then pinned and relaxed and pinned and relaxed. And you can see very clearly where this strain array comes from in a very physical way. Okay, so we end up using these close packed nanosphere arrays. There's get variations on the scale of the electronic Fermi wavelength. Like I said, if we want to see changes in conductance, we can do that with these with length scales from 10 to hundreds of nanometers, exactly the sweet spot that we wanted. We can do this over large areas. If you look back over at this picture here, we can get regions of nanospheres that are many microns long or more. Here we weren't trying that hard to get a uniform array across a chip, but you can do that if you want to. So you can get large area connected strain pockets that can be easily modified and simply. And you also get a very small radius curvature if you have 10, 20 nanometer nanospheres, which give you large strain gradients. Okay. So here's some, I believe these are SEM images of nanospheres on our substrates. And you can see that we get these close packed patterns independent of size that are quasi-periodic over several microns. So on the left here is a 20 nanometer array, and you can see that you get this kind of quasi-periodic pattern, 50 nanometer, 100 nanometers, and 200 nanometers. Okay, and you can also see that there's some defect lines in here. So you get these quasi-periodicity over the scale of, say, a couple microns. Okay, so if we have a device that's, say, 2 microns wide, we might expect 1 or 2 crystalline domains within our device. Okay, but otherwise they look pretty nice, as you can see, and they're pretty uniform, right, on the scale that we're talking about. Okay, so now what happens when we put graphene on these? So this is the same sort of nanospheres, but now with graphene on top of them, and these are AFM images now. Okay, so now what do we see? So here's a left of graphene on 20 nanometer nanospheres. And what you see is basically something that's kind of uniform. It means that the graphene is basically uniformly conforming to the top of these nanospheres. Okay. Now we see graphene on top of 50 nanometer nanospheres, and suddenly these bone-like structures and zigzag structures appear. And this is really, I found this really cool because, you know that there's graphene on there. So what is this? It turns out that all of these features are wrinkles. Okay, so on the left, on the 20 nanometer graphene, it's just conforming. You don't see any wrinkles. And then on 50 nanometer, it has more space. It's not pinned as strongly. So in between, it can release strain by wrinkling in these kind of bone patterns. Then on 100 nanometer graphene, you get more connected wrinkle patterns. And then on 200, you get these very clear lattice wrinkle patterns of graphene on top of the nanospheres. Okay, so this is interesting. It tells you that graphene is modified by the strain, that the wrinkle pattern in graphene is modified by the strain, and that different nanosphere patterns give different strain to the graphene itself, right? Because you get different wrinkle patterns, it implies that different size scales give you different strain. So now we're not just looking at strain, but we figured out a way to control the amount of strain in the graphene. So how do we determine how much strain? We go back to this Raman spectroscopy. Okay, so we go back to the Raman spectroscopy, and here, let me try this pen again, hopefully it won't pick up. You can see that we start with here's our strain line, right? Anything that moves along this line tells us that we're straining. Okay, and we start with our flat graphene. Okay, this is just a control device with no nanospheres, and this is what the ratio of the G to 2D looks like. Okay, now we go to 200 nanometer graphene, and you can see we're moving just along this line. Okay, so again, moving parallel to strain, which means as we go from flat graphene to graphene on 200 nanometer spheres, it gets strained. Okay, down to 100 nanometer spheres, it gets strained a little more. Down to 50 nanometer spheres, it gets strained a little more. Until we get down to these 20 nanometer spheres, and you can see that we have a very high amount of strain. And in fact, the amount of strain depends on the particle size. So we're controlling strain in these materials. Okay, and if we plot this average strain as a function of nanosphere diameter, we can clearly see that the smaller spheres lead to larger average strain. Okay, so this is something that we talked to theorists about. It turns out to be consistent with theory. So this is a molecular dynamics simulation by Narayan Aluru's group, our collaborator here at Illinois, and they showed that the average strain as a function of nanosphere diameter indeed got larger as you went to smaller size nanospheres. And the physical reason for this is actually relatively straightforward. It's basically that, I'll just show you without looking at the numbers, if you look at the image here of small spheres, you can see that there's a lot of graphene in contact with the smaller nanospheres. So there's a lot of strained graphene. If you look at the larger spheres, the relative area of strain to graphene is smaller. Okay, so for the small spheres, you have a larger relative area of interacting and strained graphene than you have for the large spheres, right? That means for the small spheres, you get more average strain than you do for the large spheres. And that's exactly what we saw. And you can look at this ratio and it fits. I mean, that's why you see this kind of quadratic type curve. Okay, so this fits exactly what we expect. But it also was a mechanism that had not been thought about before. No one had actually thought about how it conforms. If you thought about it in the most basic sense, it seems like it wouldn't, the strain wouldn't depend on the curvature, but it does if you look at average strain. And this is a way to control strain and also to understand its behavior on these sort of nanospheres. Okay, so that's something that tells us about how to control global strain in graphene. But we really also want to look at the strain distribution. So these simulations indeed showed that we have this strain distribution across the graphene. So this plot here is a calculation showing that we get up to 2% or more strain at the peaks of each of these nanospheres across our entire graphene device. Okay, so that means that we have periodic strain variations, which leads us to one of our initial goals, which is creating a strain superlattice in graphene. Okay, so now I'll move on to experimental evidence we have of indeed measuring this sort of strain superlattice. Okay, but first, what is a superlattice? Okay, so superlattice has been a lot in the news a lot. It's basically a long-range periodic pattern that modifies electronic band structure. So it's basically, your lattice determines how your electronic band structure. And if you add another lattice that's superimposed on top of that, then you get your original lattice plus a secondary lattice that forms due to the other structure that's there. So here you can see that we have maybe one lattice due to this bottom material. And then if you put another material on top, you get a larger lattice shown by these sort of hexagonal circles here that should give you another type of band structure. Okay, you should see in the electronics. And recently these have been shown a lot using two materials having different lattice constants, such as graphene and boron nitride, or even two different layers of twisted graphene. Okay, so when they do this, what they get is basically the Dirac point of graphene and then a shifted Dirac point due to the superlattice. Okay, so you expect two different conductance dip, one at the Dirac point, one at, I called it the superlattice Dirac point. No one really calls it that. Don't call it that. It's just a mini band conductance dip. Okay, but I call it a superlattice Dirac point because you can see why. It looks like that. But what it really means is that when you measure transport, and this is data for the graphene boron nitride device, you get the Dirac point for graphene, and then you get an additional superlattice dip. And it shows up kind of like a peak and then a dip here due to the superlattice, and that shows you that you have a superlattice across your device, and you're dealing with two different lattices. Okay, so we want to make this, we want to see how this shows up in our strain device. Okay, so now we have a nanoparticle-graphene superlattice. This picture here, the light colored circles are the original lattice of graphene, and then the dark colored circles show us the edges where the nanospheres are. Okay, and what we expect is to see strain pockets on the scale of this secondary lattice. Okay, so our secondary lattice, our nanosphere lattice, is just the size of our nanospheres. And so here I'll talk about the 20 nanometer nanospheres. And so our lattice is 21 nanometers, giving them a little space to in between them, right? But basically they're touching. So a 21 nanometer superlattice spacing there. Okay, and I just do a very simple calculation, right? You take the area of each of these red things is just equal to 4 times 10 to the 12 centimeters squared. And if we assume that we have one additional electron per supercell, right? When we talk about lattices, we often talk about how do electrons fill the bands, right? So before we're talking about how electrons fill the standard band of graphene, and now we're talking about how they fill a superlattice band. So we take this area and say, let's add one electron per area. Okay, so that's 1 over A. And that gives us 2.5 times 10 to the 11. Very simple calculation. Okay, but now we say, well, I know for graphene that we have some electronic degeneracy. It actually has an up and a down spin, right? That can go into the same area. And also it has what we call valley degeneracy due to these multiple Dirac points that you see. Okay, so for every band in graphene, you expect to have 4 electrons. So now we say, okay, let's assume we have 4 electrons for every one of these 20 nanometer areas. That gives us an expected conductance change at a filling of 1 times 10 to the 12 per centimeter squared. Okay, so there's no assumptions here at all. We're just measuring our nanoparticle size and saying we have 4 electrons per filling site. Okay, so if we measure graphene superlattice due to these nanoparticles that are 20 nanometers, we'd expect to see superlattice Dirac points at 1 times 10 to the 12 per centimeter squared, additional dips. So we make the device and measure it. Okay, so we have a device that looks like this. Again, just the nanoparticles with a graphene on top, contacts on either end, and we put a current across it, measure the voltage, and there's also the backgate, which is just this capacitively coupled silicon here. Okay, here's an optical image of the device right here, the actual device, and here's a close-up showing these kind of polycrystalline domains. But if you do a Fourier transform of this, you can still see that overall you get a quasi-crystalline structure. Okay, so in case you're worried about like, oh, it's all disordered, it's not very disordered. You can still get quasi-crystalline. Okay, so we have this device. Again, the scale of it is about a micron across. And now we measure the conductance. And so this is conductivity as a function of carrier density. For the black one here is the flat graphene. Okay, so that's graphene we don't expect any additional dips. And then the green, the magenta, and the red are three different devices that are on top of nanospheres. Okay, so you want reproducibility here. Okay, so we have three different devices on top of nanospheres and measure their conductance. And you can kind of see in the raw data, if you just look at the magenta one, it kind of goes down, and then the slope, and same thing for the green and the red one, it goes down, and the slope changes, it goes down, and the slope changes. That's a little bit hard to see here, so what we ended up doing is just normalizing the high density regions to that of a flat graphene, like here, and then seeing how it varied around the low density regions. So if you normalize the high density regions, you can see that all of the different slopes basically match up at high density, okay? And then all of a sudden you get to 1 × 10 to the 12, and the flat graphene continues with no change in slope. And the graphene on the nanospheres all has a jump. And that's both on the hole side and on the electride side, you get this jump at 1 × 10 to the 12, okay? But why is 1 × 10 to the 12 important? Because that's our filling point for our nanospheres. And so the fact that we see these jumps exactly at 1 × 10 to the 12 only for the graphene on nanospheres tells us that we're indeed measuring a superlattice due to the nanospheres, which is really nice because, you know, when you have previously what was seen as just taking 2 different layers of materials, but only certain materials worked. It really only worked for, say, graphene and boron nitride, because those are the only ones that were commensurate enough to create the superlattice effect. But now with the nanospheres, you can create any sort of superlattice in any sort of material. You just put it on top of the nanospheres, and you can see these sort of effects. Okay, so what we have here is a strain superlattice. Okay. Well, how do we know? And just to point out, you can see again, this is for graphene HBN, and this is for our devices, the nanoparticles, and you can see very similar sort of behavior. Okay, so, okay, I said this already, but basically, you know, you can compare the graphene HBN to what we have, and, you know, they're limited by this lattice constant. We have a wide range of tunability. Even though the graphene HBN is atomically precise, we do have some quasi-periodicity that allows us to see the effects, and it can be useful for any sort of material structure. Okay, so how do we know that we're really, you know, now we have to worry a little more about what, you know, we're not perfectly ordered, maybe there's some charging effects, how do all of these things come into play? So that's why we worked with our theory collaborators to see, okay, if you simulate the disorder we have, if you simulate charging effects, how does that affect our features to make sure we really have what we think we have? And so we worked with my longtime collaborator, Matthew Gilbert, who's in ECE here at Illinois, and his group does really nice quantum transport simulations where they showed how the superlattice conductance changed as a function of strain and disorder. And you can see, for example, that for a perfectly ordered sample, you get these very deep secondary dips. But for a disordered sample, you can still see the dips in the way that we see them. So, you know, if we have more order, we could see clearer dips, but it's reasonable to see what we actually do. Okay. They also showed that the effects we see are inconsistent with charge effects, right? You do worry that there's random impurities that may be on top of the nanospheres, and that variation in potential can lead to what we see. However, the key word is random impurities, because impurities on top of these would be to have random magnitudes. And you can show that these sort of charge fluctuations and residual carrier density don't lead to any sort of superlattice effect like we saw. Now, they could see this in their calculations. We also did the control experiment where we took graphene and we spun nanoparticles on top of it, right? Because if there's a charge variation, then the charge difference should be there with the nanoparticles on top of the graphene or the graphene on top of the nanoparticles. It shouldn't matter. But when we put the graphene below the nanoparticles, we didn't see any superlattice effect. When we put the graphene on top of the nanoparticles, we saw a strong superlattice effect. So again, that all of this implied to us that our superlattice is by and large due to strain, which is one of the first examples of a strain superlattice. And finally, we showed that when we thermally cycled these, now again, we've just kind of pressed the graphene on, and so when we thermally cycle it, the graphene can slip a little bit and relax, right? So what we expect is with thermal cycling, we get reduced strain. And indeed, that's what we see. When we thermal cycled our sample, this is on the left here, this is this is our original sample here. It's pretty highly strained. And then we heated it up and cooled it down again. And when we did that, it reduced its strain. Okay, it went to there. And again, you can see it didn't change doping very much, but it strongly reduced strain from something like a 20% shift to a 2% shift. And then when we went back and measured our superlattice dips, indeed, you see that the less strained sample had a smaller superlattice dip. Okay, so again, this implies what we're seeing is due to changes in strain more than anything else. Okay, so we also want to see, we're looking for pseudo-magnetic field effects. These should be evident in the magnetic field behavior. Is the next thing I'll show. What do you expect in the magnetic field behavior? Just very quickly to refresh on this. I always get confused when I see these diagrams because they're very pretty, but then I realize I don't know what they are. This is a Landau fan diagram. Okay, so for 2D systems in magnetic fields, electrons have cyclotron motion, right? Electrons move perpendicular to a magnetic field and they just go around in a circle, okay? So the Hall effect, the quantum Hall effect is basically when you have one flux trapped in a cyclotron orbit and all of these orbits basically condense into a ground state. Okay, so these Landau levels will fill with electrons and the filling of these levels will vary both with magnetic field because you can fill more flux lines, right, per magnetic field. And they also change with electron density because you can fill more electrons with more magnetic field, with more electron density. Okay, so this plot on the left, these bright lines basically show, I believe, these are the low resistance lines. And so these are in between these filled Landau, and then these darker blue lines are the Landau levels. And what you see is that they start at some value, and then as you increase density or increase magnetic field, they just vary, they start filling linearly with either field or density. Okay, so here's what you see from a Hall effect. You get a drop in resistance when you a drop. These are edge resistance. I don't want to explain Hall effect, but anyway, you get a drop in edge resistance when you don't have a filled state, and increased resistance when you have a filled state, and then this fills linearly with both field and density, which you see here. And so that's this Landau fan diagram, which tells you that you have a quantum Hall effect and Landau levels. Okay, so this has been seen in graphene, but when you have a superlattice, what you expect to see is this kind of Landau fan diagram for around the Dirac point, but then secondary Landau fans around these secondary Dirac points, these superlattice points. Okay, so what do we see? Indeed, when we have no strain on our control device, we see these Landau fans. Okay, so this is a high resistance point. This is a low resistance point, and here these numbers refer to the filling of the Landau levels. So this blue region is a plateau of 2, this is a plateau of 6. And so this is exactly what you expect for clean graphene under a magnetic field with no strain. Now we take a device that has a lot of strain. How do we know the strain? We do Raman spectroscopy. We can't really control this. We're keeping the nanoparticle size the same. We're measuring Raman to see what the average strain is. Here we have about 2%. And what we see are these strong secondary Dirac points. Okay, with that dispersed in magnetic field, just as you'd expect for a Landau, for a superlattice. Okay, so this is really nice. This shows us that we have a superlattice with secondary Dirac points that dispersed with magnetic field as expected. Now it's interesting, what hadn't been seen before is for weaker strain, we see some in-between behavior where we have what looks like a strained superlattice dominating at low magnetic fields, and then a standard Landau fan diagram coming into play at higher magnetic fields. So what we believe is happening here is we're having an interplay between a pseudo-magnetic field dominating for the low fields and then the external magnetic field dominating for the high fields. Okay? And indeed, when we work with the theorists to simulate this behavior, what they found, they're able to simulate, these simulations look very similar to what we have, but the simulations assume a relatively high pseudo-magnetic field. And in fact, you can see the simulations here. This is for no field, and it's just a standard fan diagram. And then as you go to higher fields, you get these regions like we have of interrupted Landau fans. And so the behavior we see is something similar to something like an 8 Tesla pseudo-magnetic field on average across our device. Okay, or 5 Tesla, 5 to 8 Tesla, I don't know. I think it's 8 today. Last time I thought it was 5. Okay, so this is exciting. Like we indeed can see some effects of pseudomagnetic fields. We have controllable strain. We have secondary Dirac points. We have these interesting strain superlattices that are flexible across devices. The next things we want to do are, say, improve the periodicity to get larger pseudomagnetic fields, and maybe see these strain-induced recursive structures due to the field. Due to the superlattice. One of the new things that's come up recently is that they expect to see what are called flat bands due to correlated effects. Now, this is a paper that came out in June of this year. It's another scanning tunneling microscopy paper out of Eva Andre's group. But what she did is she put graphene on a surface and saw these wrinkle structures that appeared. And these are sort of naturally occurring periodic wrinkle structures. And then their calculations showed them that you expect to see not the standard, intertwined band structure that you'd get from many materials, but rather these very kind of, around the Fermi energy, you get these regions of non-dispersing bands. Okay, so non-dispersing bands means you have very strongly suppressed kinetic energy, which means that you very likely have enhanced interactions. And so this has been a field, something that's really booming in condensed matter physics, this idea of very strong interactions around the Fermi energy due to what are called flat bands. But flat bands are generally really hard to engineer, okay? But it turns out they may be engineerable in strained graphene like you see here. And in fact, when they did scanning tunneling microscopy, what they saw was a gap appearing around zero energy and shifting of spectral weight to the left and the right of the Fermi energy at higher gate voltages, which is consistent with what they'd expect for some sort of correlated effect due to a flat band. So this was really exciting to us because, again, this is STM, but these sort of effects have not been seen very strongly in transport, and that's the next thing we want to look at in these nanoparticle graphene devices. And of course, we're interested in other materials. So, if you can globally control strain in graphene, you can use similar techniques on this whole zoo of 2D materials that have been appearing recently. So, here's just showing some of these things. There's the chalcogenides, Bisco. You can stack these materials. You can create many different types of electronic structures from stacking and manipulating, and just every day new 2D material seems to come out with different functionalities. And so we're interested in taking many of these and saying, okay, what happens now when we strain these? What new effects can we induce? And just as an example of an effect, oops. This is a paper that came out some time ago. It's showing how if you take molybdenum diselenide and you strain it locally, it becomes a really good solar energy funnel. Okay, so they put an electrode on top, and they could actually funnel light into this little region that was highly strained. But note here, they did this by applying strain with just a single external AFM tip. Okay, so again, if you can do this globally, you can get a device out of it. Okay. And there's a zoo, again, the zoo of 2D materials and all sorts of potential devices and really interesting physics that can be obtained these days by wrinkling, stretching, bending, and overall controlling strain for devices and for physics. Okay, so to summarize, I talked about substrate engineering as, I hope, an effective way to really tune strain in 2D materials. I started out by talking about graphene on pyramids and pillars, strain arrays, electronic confinement. I then talked about graphene on these nanosphere arrays, where we saw strain superlattices, pseudomagnetic fields, really made a tunable strain device platform. Our next steps are to look at potential as strains as sensors, as well as looking at new electronic functionalities by varying the materials and improving the periodicity. And I will end with, this is really my last slide. I'll end by saying that, just to mention, this work is part of the broader effort at the Illinois MRSEC, that's Materials Research Science and Engineering Center. I happen to be director of the MRSEC, so I have to plug it every time I can, because it's a really great center. But this MRSEC has two interdisciplinary research groups, and one of them is specifically looking at active interfaces between highly deformable nanomaterials. And so the goal of this is a collaboration of 8 to maybe 10 PIs these days, many students from different fields, mechanical engineering, ECE, chemistry. And our goal is to look at the structural, mechanical, and electronic effects of deformations of 2D structures across all length scales. And so you can see some of the papers that have come out of the group, including looking at beautiful TEM images and modeling of bending in few layers, graphene, ultrasensitive detection of biosensors. There's our paper. So all of this, there's a whole group of us here working on the physics behind these sort of deformable nanomaterials. And with that, I'll acknowledge the people who did this work, our funders, MRSEC, the ARO recently in the engineering part, and here are the papers that I talked about today. And with that, I will end and I will take any questions. Thank you very much.
Thank you, that was wonderful. So I guess we'll jump straight to questions. And there is one in the chat already from Samuel Schwab. Do you want to ask your question out loud? You can just unmute yourself and ask.
I'll stop sharing so you can see each other.
Yeah, sure. So fantastic talk. Thank you for doing this. So I just had a question about the statistical variation that you saw on the strain.
Yes.
When you put this graphene blanket down on the spheres,
yes.
It seems like the kinds of patterns that are formed from that are very, very varied.
Yes.
So is there some kind of method that you could do to help mitigate that? And your second to last slide gave me a thought there of using an AFM tip to sort of push in between the spheres. Is that something that's feasible, or would it just sort of break right through the graphene?
So a couple of things. So yes, it would be nice to be able to control strain locally a little bit better. The reason that we ended up using these pyramidal and nanosphere structures is that even looks like it's kind of random. If you put a 2D object on top of a pyramid or a small point, it is forced to kind of wrinkle in very specific ways, right? And that's the wrinkling that we're looking for to create these pseudo-magnetic fields. And so in the same way that for the AFM experiments, they had these little nano pillars, the way that the graphene conforms to a pyramidal point is what leads to these predicted fields. And so we believe that, the very local deformation of the graphene sticking and then bending off is what leads to the pseudo field effects. What it does after it sticks away from the apex and when it kind of folds and bends, we haven't modeled, and that's much more, I would say even that's not quite random, as you saw from the images of the graphene on different size spheres and how the wrinkles form depending on what size the spheres were. So I guess I'd say that there's going to be some variation there, but there's also, it also definitely seems to fit some of the modeling, if that answers your question. Now, with regards to pressing down an AFM in between, we could do that. And actually a lot of measurements were done with graphene pressed down by an AFM tip and then modeling what you saw in the conductance directly across it. Our goal was to move away from that a little bit. An AFM tip is just a sharp tip, right? So what we have are basically inverted AFM tips. So we're trying to move away from having to do something locally to inverting it and having it just naturally form the strain that we want. Does that make sense, Samuel?
Yeah, it does. Great. Thanks so much.
Okay, so then there's a question from Arvind, which he says he can't read because he doesn't have audio. So I'll read it out loud.
Okay.
Would you be able to observe more clear conductance dips versus gate voltage at lower temperature, maybe?
Yeah. I'm trying to remember how much of this what temperature were we? I believe that, did I even say what temperature we were? We were at low temperatures. We weren't, I believe that this was either done at 1 Kelvin or something like 800 millikelvin, I think. So yes, it's possible that we could see something more clearly if we went to much lower temperature. I believe that most of the spread that we saw is due to disorder, actually, right? So my feeling is that even if we went to much lower temperature, that we're dominated by some of the charge disorder and some of the. I mean, this is what Samuel's question was: is there variation in the pinning of the graphene? And that indeed is part of the disorder we're talking about, some of the local disorder in the pinning. And so I think that we're dominated by that more than temperature. We are going to lower temperatures actually now. We're just getting our post-COVID fabrication and everything back up again, both to look for these effects, but also to see some of these more interesting flat band effects, which I do believe will only happen at much lower temperatures. Because if you're looking at interactions, we'll have to be at much lower temperatures to see. So yeah. Okay, so then there's a question from Walter. Do you want to ask that, Walter?
Sure. So thanks for a very interesting talk. I've been interested in, some other 2D materials that under strain would have interesting properties. So maybe a way to go about it. So one of my questions is, how large a strain can you achieve, you think, with these methods? And is it always a tensile strain? And then I have another question, which is perhaps a little more technical, but I'll let you ask the first one first.
Yeah. So, I mean, calculating the amount of strain has been hard because it's local. So that, our theory collaborators, and let me see how much strain that they, I always think about this. I believe, it's usually a few percent is the maximum strain that we'd expect at the apex, which is actually relatively big, but it's a few percent actual local strain on the graphene. Now, when we measure it, we're measuring an average strain, and so our average strain is more like 0.1 or 0.2%. But then if you just work that back, because the Raman, we're doing it with Raman, and the Raman spot size is bigger. It's I don't know, half a micron or something like that, and so we're averaging over 10 nanospheres. And so we're seeing everything, and that's 1%. And then you can work that back. Sorry, that's 0.1%. You can work that back and get a few percent on there. It is always tensile.
A very small region.
Yeah.
Percent is over like, a few nanometers.
Yeah, that's right. That's right. Yeah. That's exactly right. And the tensile strain, we do always see tensile strain at the top because it's pinned. And so when it's pinned, it gets pulled at the top, and then we believe it relaxes in between. Yeah.
Okay. So is it relatively homogeneous strain?
That's how we calculate it. I mean, that's how we, I mean, so, this, let me find this thing. This is a, this is the calculation that was that sorry, you can see it here. I mean, you can see it, right? So this is basically how it's calculated. And so you can see both of your questions sort of answered here, is that, the calculation is a couple percent strain at the top of the spheres. And it looks like it's relatively, okay, this is theory, and I believe their spheres here were 10 nanometers in size. Maybe there are 10, maybe there are 20, but you can see it's localized over maybe 5 nanometers. But we have 20 nanometer spheres, so yeah. 5 nanometers is a significant fraction of 20, yes. Right? So this is what we guess that the strain profile looks like approximately.
Okay.
But this is a simulation. It would be nice to have a better way to measure it directly. Most methods that I've seen will average over a few spheres at a time.
Okay. So when this,
so I think maybe just in light of the time, maybe we can continue that discussion in private.
Okay.
I'll stay around after the official time. I'd love to talk.
Just a few minutes anyway. I guess there's one more question from Annette, so maybe we'll just take that one and then wrap.
Well, I guess that question doesn't make sense as much now because I didn't know it wasn't a direct measurement of the strain. It seems that it's a theoretical calculation. I was trying to see if the gradient of the strain made a difference versus like just the size of the contact point. If that makes any sense.
Yeah, I mean, there's both, right? I mean, we do directly measure strain with Raman spectroscopy. It's just that it's an average strain, right? So to do a direct strain, we'd have to have a probe that works at the few nanometer scale. And we do have STM results on this. It's just STM on something that's dirty like this is really hard, and so it was really, we just couldn't get enough atomic resolution. We do have preliminary results showing really nice Landau. We're looking for flat band behavior in the STM on these, but it was hard to get the local strain. So, but tell me, what was repeat your question again, please?
Okay, sorry. I was just wondering if it was the gradient of the strain that makes the difference, or just kind of like a total strain, like a total, yeah. Like, does that make sense?
Yeah. For pseudo-magnetic fields, it's the gradient of the strain. Let me, I mean, maybe this doesn't make sense. I don't know. I put this in a very small thing, right? So I put this here, and we have this very, right? So if you look at the very bottom here, this is how this, this is just specifically for pseudo-magnetic fields, but it assumes a non-uniform strain field, right? And then to get the pseudo-magnetic field, you basically have to take a gradient of that. So it's not, okay, so it's not the gradient of the strain. It is actually the strain field that matters. If that, for this sort of thing, right? This is just a strain field directly as a function, not a gradient strain field. And that strain field itself goes directly into the vector potential. So all that matters is that you have the strain field. And this is what I keep pointing to. If you look here, oops. If you look here again, we've been talking about how do you model it and what does it look like? This is and this is a topography image. This is not a strain image here, even though it looks like a strain image. This is topography, right? But it does show you that this is the sort of feature that they have and the length scale. And it's not perfect, and it's not a perfect pyramid. And the graphene does seem to conform to it pretty well just at that point. Although at the bottom you can see graphene. And what's happening here is I'm assuming that graphene releases strain at the bottom, and then it sticks to the substrate in between. Right, but from this particular, just experimentally on here, they could directly measure these Landau levels comparable to a 300 Tesla field. So, this experiment, at least, ours is complementary to this, in that this shows that you don't need a perfect bubble, right? And you don't need a gradient, and you just need something that graphene is conforming over a small enough region and locally strained over that region to lead to this effect, and then you'll see it. That's what I took from it at any rate. Does that answer your question somewhat?
Yeah, I just was curious because if you're going for a gradient, right, you'd have a different structure, base structure.
Yeah, we're going for something global and uniform. So and there is a question, in between, does it just for, obviously, so here's the thing, if you have tensile strain, then you have to have compressive strain somewhere. You can't just, somewhere it has to stretch and then compress, right? And so somehow that doesn't seem to be, we've just modeled the tensile strain at the top of the pyramids. I don't know what electronic behavior is due to wherever it compresses right before it relaxes, or whether it relaxes uniformly and that's gradual enough that that doesn't lead to an electronic effect overall. These are all really open questions. And this stuff, as far as I know, that hasn't been modeled or studied in any detail. Yeah.
That's a wonderful note to end on, that there's so many open questions. I think maybe this is a good place for us to end the formal portion of the talk. And Nadya has kindly agreed to stick around for a little bit longer, so we can continue the conversation in private as well. But let's take this moment to generate some underwhelming Zoom applause for a really wonderful talk. Thank you so much.
Thank you. My pleasure.
So I think I'm going to stop.